So it's my pleasure to introduce again Kai-Uwe Books, who's today talking a bit more about the bodification.
Well, yeah, that, and I will also start on the dimension of the Torelli group. But since I advertised the bodification, I think I owe you a little bit of a description. So how does this work? Well, recall outer space. There are these simplices in outer space. For every graph gamma, a marked graph, you have the simplex where you assign a metric. So each edge of gamma gets a length, and the sum of the length is 1, and none of the length is 0. So it's an open simplex, and the edges, the edge lengths are barycentric coordinates. So if you think about the theta graph has 3 edges. So you get a triangle. So here's that triangle. And that sits somewhere in outer space. Now, what does it mean to go to a face? It means you shrink an edge until its length becomes 0. That's no longer within the open simplex. You move to the closure of that simplex, so to speak. And on the graph level, you see that you shrunk the edge completely away. So the combinatorial type of the graph changed. So at an edge like at this edge, you actually see no longer a theta graph, but just a figure 8. So if you want to go further to a vertex, right, then you're encountering trouble, because if you shrink a loop to 0, you're not only changing the graph, you're also destroying the fundamental group. So this vertex here, the top vertex, and for that matter, none of the vertices of this simplex, is actually a point in outer space. So there are missing faces in the open simplices. Not all of the faces of an open simplex are actually realized in outer space as the simplices for other graphs. So for instance, if gamma is a rose, none of the faces is there in outer space. So if you start with a rose, you cannot collapse any of the faces down to 0. You can shrink them, but not to 0. So this will be an open simplex, and its boundary is not in outer space. So that's the reason why outer space is not co-compact. So, and here's another example. That's an interesting example, because the asymmetry of the graph really shows. So this graph has 2 types of edges, the loops and the non-loops. You cannot shrink the loops, but you can shrink the non-loops. So one way of, so this is 4 edges, so it's a tetrahedron. And this tetrahedron has 2 faces, 2 triangle faces that correspond to shrinking the non-loops. Those could be shrunk, and you would actually have faces within outer space. But shrinking the other 2, either one, would take you out of outer space. So you can draw this and in such a way that you say, okay, the front facing, the faces that I see are actually there, but the faces in the back, they are missing. So how would you go about bodifying a space like that? Well, the obvious idea is, well, if this looks like simplices and it has just a few, and there are just a few faces missing, just glue them in. Just make these simplices honest to God closed simplices. What's the problem with that? Well, depends on what you want your bodification to do for you, right? The problem for our application to virtual duality is when you add a simplex, when you fill in this vertex here, if you really make these solid, you can extend the group action, but the stabilizer will no longer be finite. And the reason is that this vertex here is shared by the neighbor, and by that neighbor, and by that neighbor, and by that neighbor, and you get a whole slew of things, and all these translations that take the blue triangle to whatever, they all can fix this vertex here, and you get a really, really big stabilizer for these points at infinity. So if you modify like that, you don't get a co-compact space to act on with finite stabilizers. So all that it will compute the rational cohomology for you is gone. So that's why you don't want to do that. So instead, you need to do something about these vertices. And Mladen and Mark had this idea of, well, okay, so let's suppose we have this simplex here, and we want to add stuff at the vertices that are missing. So what we can do, instead of just putting a point in there, we sort of think of what does it mean to go towards infinity, and then we distinguish the different directions from which we may approach that point. So this is like a blow up in algebraic geometry where you also take into account the tangent space, right? So you instead of putting just a single vertex in here, they actually glued in some tiny interval to keep track. And I tend to draw it in a circular way because in my mind, it just keeps track of directions in which you may approach this point at infinity. So they turned this triangle into a hexagon. And they figured out how to deal with this for more complicated graphs. And looking at the graphs, you can define a hierarchy of core subgraphs, and that defines the strata for the compactification, for the bodification. This is very much in line with the Borel-Serre compactification for the symmetric space. You start with the space and you glue stuff to it at infinity. So that's what Mark and Mladen did. There is historically, so the best Wiener Fein compactification, bodification, that is the analog of the Borel-Serre bodification. And there is a whole competing approach in the classical way, namely there is a paper by Grayson, and he had this idea of, instead of gluing stuff to infinity, he had this idea to retract from infinity. Now the paper is by Grayson, but Karen tells me that she remembers talks. She remembers that Ash gave talks at the time promulgating this idea. So, and if you, let me just put that up. If you look at these simplices, there is a way of actually doing sort of the Grayson thing. What you do is you shave off faces at infinity. So let me talk about shaving off faces from infinity a little bit. So what I mean by shaving up faces from infinity is just this. You have this triangle. Certain faces are missing, so they are infinite faces. These are the faces at infinity, and you want to shave them off, which means you just take a razor and cut them off. So you would be left with this hexagon. And it's not a coincidence that it looks like the hexagon from Basvina and Fane. And if you have if you have a simplex where all the faces are in infinity, you actually have to shave them off. You have to shave off all of them, but you could be stupid. So you want all of those faces to actually leave a trace, to be actually visible after shaving things off. So here, if you just took your razor and shaved off the vertices just a little bit, but the edges a lot, then after shaving off the edges, there wouldn't be any traces of the vertices being shaved, right? They would be just, so you have to be careful. You want to be closer to the edges with your shaving than to the vertices. So, and there is a way of formalizing that by saying, okay, so choose a small number epsilon and then shave off something that depends on the dimension of the face. And if you do that, for every simplex, you shaved off the stuff at infinity and you get a deformation retraction of that simplex. You can actually just push things in here. So that works. This is a deformation retract, and you can make that equivariant. So now that you have these joules, you can glue them together in the same way that you glue the simplices for outer space. And the reason that works is, why can you glue these things together? Well, because when you glue two simplices together, the face along which they are glued doesn't lie at infinity. So you didn't shave that off. So the joules still connect to that gluing face. And so the joules are still glued together in the same spot, in the same way. So, so that's why you end up with an equivariant co-compact deformation retract of outer space. And that's precisely what Grayson also ended up with. It's an equivariant co-compact deformation retract. So in particular, it's a subspace, and therefore it inherits the finite stabilizers, right? You have finite point stabilizers, you have finite cell stabilizers. Now, what does it look like? Well, okay. So here's a little picture. This is probably an instructive picture, and I just want you to see that. So the graph is the one that we already had. So the back faces are missing. This is how it's drawn, and the front faces are there. The front faces are rose faces, because if you collapse one of the two edges in the middle, you get to a rose. For a rose face, it's easy to see what the Joule is. The Joule of a rose is a permutahedron. So it has n factorial vertices, and these vertices encode an order of the petals. So the way, let's have a rose face here. So that's for this graph. You shave off everything. So you shave off the edges and you shave off the vertices and you get this little hexagon. So the way this, let's, so the way this vertex here encodes an ordering is the following. This vertex knows which corner it is closest to, and it also knows which side it's closest to. The fact that it is closest to this edge means, well, there is one of these petals that you blew down first. And the fact that it is closest to this corner means now you know which edge you have to blow down second. So this here is the first petal to blow down. And this is the second blowdown. So the vertices of a Joule for rows correspond to orderings of the petals. And that's what a permutahedron encodes. And if you have an arbitrary simplex, then you can see, and this is just the picture, then you can see that all the vertices of the Joule are actually lying within rose faces. And the vertices of the Joule is the convex hull of its vertices, and every vertex lies in a rose face. So it's really the convex hull of the rose faces. So all that matters is really understanding the roses. And from there, you actually, and I don't want to spell that out now, but from there you get an explicit, a more or less explicit nerve cover argument type of thing that tells you that rose complex that I discussed on Monday is really G equivariantly homotopy equivalent to the Joule complex. Now, why were we looking at this in the first place? Because after we went through the argument, of course, we saw that just for the connectivity at infinity, you don't need Joule space, right? The Joule space, the bordification is a picture, the argument, the space for which you argue that it is n, 2n minus whatever connected at infinity 3. What was the connectivity at infinity? 2n minus 5, right? Something like that. That it is 2n minus 5 connected at infinity. The space that we did that for is Rho space. So why bother with Joule space? Well, first of all, what was the motivation for Besbina and Fain? The motivation for Besbina and Fain to actually work with the to find a bodification was as follows. First, Morse theory on the spine is difficult. And the reason is, if you are, so there are geometrically, the geometry of outer space suggests what should be descending directions. Namely, they come from folding edges in graphs, continuously folding edges in graphs, to reduce the length of various loops, right? To make loops shorter. So if you have inside gamma, a picture like this, you have a trivalent vertex, and you have a loop that runs around like this, and you want to reduce the length of that loop, what you could do is you could make the initial length edge longer and this edge shorter, right? Stuff like that. So that would make the loop shorter. And that's a motion in outer space that reduces the length of a loop. And it turns out if you look at geometrically natural Morse functions, then they will leave the spine. So naturally descending directions don't stay in the spine. And so you want to make the spine bigger to smooth out singularities for Morse functions, because if you want to define a Morse function now in the spine, you would have to constantly reproject your flow into the spine. And the way that shows up formally is by having a Morse function that is not well behaved, that has singularities. So if you have more space to work with, you can smooth out those singularities of the Morse function, and you get a better Morse function at the cost of making the space larger. That was the problem that Laden and Mark solved by looking at their bodification. And Peter, Karen, and myself, we went around this problem in a similar way. Instead of working with the spine, we looked at Rho's complex, which is also bigger. That's one thing. And the second motivation, and that's why we actually wanted to look at this, is of course that the boundary might give an interpretation, a geometric interpretation of the dualizing module. That's at least what happened in the classical case, but that uses Poincare duality, and for outer space there is no such thing. And so far, nobody was able to actually make inroads on this idea. However, we just decided at the time that the more pictures you have to look at, the more likely it becomes that someone might have an idea. So that's why this boardification may still be useful in the future at some point. Although as of now, nobody knows how to deal with the problem that outer space simply isn't a manifold. Okay, so now I'd like to turn to the second topic. Are there questions regarding the boardification? No, I do not. I should say that I have no idea where the chat is at, because the chat is not on my screen.
I'm monitoring the chat. There's nothing in the chat, and we are content here as well.
Okay.
If somebody wants to speak up on Zoom, they will.
Okay, good. Then I'll just move on to the second thingy. Save. What about save? The dimension of the Torelli group in out of N. So first of all, what is the Torelli group? You have out of N. There is a natural map to GLNZ. There are two ways, at least, to think about this map. One way is to think about it, well, Z to the N is the abelianization of the free group. So if you hit an automorphism of the free group with the abelianization functor, you get an automorphism of Z to the N. And another way of thinking about this is geometrically. Odd of N is the self-homotopy equivalences up to homotopy of a rose or of any other graph with that fundamental group. And you can look at what that automorphism induces in homology. The homology of a rank N graph is Z to the N, so you get an automorphism of Z to the N. So there's this natural homomorphism, turns out it's onto. But for us, the Torelli group is the kernel of that homomorphism. And the most important little nugget to know about this kernel is that it is torsion-free. So why do we call it the Torelli group? I should say there's an alternative notation for this. This group is also very often called IAN, IA for identity on the abelianization. I don't think that that is a name. I think that is a notation only. We call it the Torelli group because for the mapping class group, there is an analogous subgroup. It's those mapping classes of a surface that induce the identity in the homology of the surface. And I'd like to convince you at some point that the cohomological dimension of the Torelli group in out of N is 2n minus 4. So there are a few observations. I should also say this is very sharp. This is sharp in that the homology in that dimension not only is not equal to 0, it's actually not even finitely generated. But a quick way to see that the cohomological dimension is at least 2n-4 is to not bother about infinite generation. It's just sufficient to find something in there. And one thing you can find is a torus of dimension 2n-4. And inside the group, you need to find a copy of the free abelian group of rank 2n-4. So how do you do that? Well, you fix the last two generators. You look at automorphisms that fix the last two generators. And the first two generators, you multiply from the left and from the right by powers of commutators. So you take the commutator of xn and xn-1. If you multiply a generator by a commutator of two others, in the abelianization, you will not be able to see that because the commutator just goes to 0. So in the abelianization, this here is just sending x1 to x1. Although in the free group, you did something to the left and you did something to the right. And since you are using the same element for these powers all the time, these automorphisms commute with one another. And if you just work out what they are, they add up to giving you this one. So that's how you find a copy of the free abelian group inside out of n. And it gives you a lower bound for the dimension because the cohomological dimension of the free abelian group is just the rank of that group. So that tells you that the cohomological dimension is at least this much. The work is in seeing that it is at most that much. So what's an upper bound? I claim an upper bound comes from geometry, and it's just 2n-3. That's the obvious upper bound. So how does that work? Well, recall that the Torelli group is torsion-free. And recall that out of n acts on the spine with finite stabilizers. So those stabilizers intersect the Torelli group trivially, which means that the Torelli group acts freely on the spine. So if you look at the quotient, that quotient is a classifying space for the Torelli group. Right? It's a cell complex, it's a CW complex. It's not necessarily a simplicial complex because there might be self-identifications going on. Things might be weird, but it's a CW complex with fundamental group Tn because the action is free, and Tn acts as a group of deck transformation on the spine, and then the canonical projection map becomes a covering space map. Sort of. Maybe, maybe not. No, it does. It does. Okay. Yeah, you just have to be careful about how large an evenly covered open set can be. So now the dimension of this thing is obviously the same as the dimension of the spine, and there's this Euler heuristic count argument telling you that the spine is 2n-3 dimensional. So the geometric dimension of the Torelli group is at most 2n-3. And so now we know that the cohomological dimension of the Torelli group is either 2n-4 or 2n-3. And the question is really, which is it? And the answer is, it is 2n-4, and the way to prove this is to construct a homotopy equivalence of this complex Yn to a CW complex of dimension 2n minus 4. What happened? Can you hear me?
Yes, I can hear you.
Can you see my screen? Because I lost the green bar.
I can still see your screen.
Okay.
We can see the third page. No, the fourth page, sorry.
Okay. I'm totally confused because the UI of Zoom totally disappeared
Oh, shoot.
from my screen. So, okay. Strange. Let's just.
Can you move your mouse to see if we still get your, yeah, we see your mouse moving.
Okay.
Carry on.
Interesting. Okay, thank you. So this complex Y, how do you describe the points in there? Well, it's the quotient of the spine, so it should consist of marked graphs mod the action of the Torelli group. Now, what does the action of the Torelli group do to markings? Well, keep in mind, out of n acts just by changing the marking of a graph, right? So it only acts on G, it doesn't act on gamma. So two markings differ by an element of the Torelli group if and only if they induce the same map in homology, right? That's what is written here. So if you have two markings that induce the same element in homology, you can look at the quotient of the you can look at a change of markings. You do that in the fundamental rows, and you see, that change of markings has to be an element of the Torelli group. And vice versa, if you change the marking by an element of the Torelli group, it's multiplying the map in homology with the identity map in homology. So this is how you can characterize the orbits, the Tn orbits of a marked graph. It's just a graph with a homology marking, with an identification of the homology group of gamma with the homology group of the fundamental of the standard rows. So points in Yn are homology marked graphs. And you can visualize homology markings as follows. So you have your marking, and we want to consider what it does in homology. So if you look at a petal, let's say x2, right? We orient that in some way, and then it runs around in our complex, in our graph, and it comes back, and it does weird things, and then finally it goes on like that. So what happens here? If you look at the edge E, this edge was crossed by this loop 3 times. But there are 2 times where you got that edge E also carries an orientation. And you look at the number of times that it goes, that the blue loop goes with the orientation, and the number of times that it goes against the orientation, and the difference, the net total of traversals, where traversals against the orientation of the edge are counted negative. That is a number. It's the coefficient of that edge in the cycle that corresponds to that loop x2. So each petal is a cycle in the rows. The homology marking maps that cycle to a cycle in gamma. That cycle is well defined because in gamma there are no two cycles differ by a boundary, right? Something like that, and there are no boundaries. So this is a unique cycle, and you can look at the coefficient of an oriented edge in that cycle. And for every coefficient, you just write that down. So this edge, in the end, just gets a labeling. We call that a label, and it's counting how many times x1 goes through that edge, net total, how many times goes x2 through that edge, net total, and so on and so forth. So here's an example of a homology labeled graph. Oops. The first edge, x1, goes around this guy, and it doesn't do anything else. x2 goes to the middle loop, and x3 goes to the final loop. Now, of course, in the actual marking, this would probably look roughly something like this. The first edge would have to go something like that, and it then traverses this guy backwards. So on this edge here, on this edge, you get a net total of 0 for x1, because the two directions cancel out. So this is a way of writing, of annotating a graph with labels for oriented edges in such a way that it tells you exactly what the homology marking is.
So I don't know if that's useful for later, but so a homology label is just a basis of the homology of that graph.
Yeah, right. And yeah, you can think of it that way, yes, because the petals of the standard rows form a natural basis for that z to the n, and the map G star in homology just takes that basis to a basis for the homology of gamma. So it's a graph together with a distinguished basis for its homology. Yeah. Now, this picture about just loops running around tells you one more thing, namely, if you look at a vertex and you look and your edges in the graph carry an orientation, then you know that that if you add up all the incoming labels and you add up all the outgoing labels, the sum of those labels have to match. They have to be the same. And the reason is that every individual petal gives you a loop, and a loop that goes into a vertex also goes out of that vertex. It doesn't get stuck in the vertex, right? So at every vertex, the net total of all the incoming and all labels matches all the outgoing labels. So here's an example graph that is just gotten from the standard rows by blowing up this vertex, the black vertex, into two edges. And now we can just use this observation to actually figure out what the labels of these edges are. So let's look at the light blue edge first. The light, oh wait, that was, I already decided on a color, right? So this is, let's call this orange. So how would you compute the orange label? Well, what is the first entry? So the first entry corresponds to the blue petal. The blue petal is x1. So x1 goes into that vertex, and it has to go out of that vertex as well. It doesn't go out of that vertex via the green or the red edge, so it has to go out of that vertex via the orange edge. So this will be 1. Now look at the second edge, the red one. The red edge already goes out of that vertex via the red edge, so it has to go into that vertex via the orange edge because it doesn't do via the blue or the green edge. So there has to be a -1 because of orientation, right? The red loop that I didn't, that is silently to be completed running like this, right? And here it is running against the edge. And the same thing happens for the green loop. So there will be a -1 here as well. And here we can do that for the, now I have no idea what to call that color, but anyway, pink, is that pink? Whatever. So there you should get 1 because the blue loop is aligned with this thing. You should get -1 for the red, and you should get a 0 for the green because the green loop doesn't really use that edge, right? The green loop goes like this. It's blown up like that. So you can use this to see what the labels of a blown up subtree are. If you blow up a vertex and you insist the marking is not to change, I really want to look at a blow up of a marked graph, then you can work out what the labels of the edges are that you blow up. And the second observation is they always are just linear combinations of the labels that you had before, and the coefficients are +1, -1, or 0, because the previous label either contributes incoming with the direction, against the direction, or it's not flowing through it at all. So there's a word of warning. Y is a CW complex, and we will discuss cell structures on it, but it's not a simplicial complex. And here's the example from before already provides us with a counterexample to simplicial things. We can see a diagon in this space. Namely, here's a graph that can be blown down to this, to the standard rows. Let's not label the standard rows, in 2 different ways. Namely, you can blow down the middle bottom edge, or you can blow down the middle upper edge. And it will get you down to the same marked rows. And these 2 forest collapses are 2 different morphisms in the category, and they really give you 2 different edges, with the consequence that there is a circle, right? There is a little loop. And you can actually think about it in those terms, right? The way you can think about this as a loop is, well, you have your graph with 2, and where these 2 circles touch, that's sort of a base point. And then you have a third circle, and that circle, you can slide around one of those circles all the way. And that corresponds to blowing up one edge and at the same time blowing down the opposite edge. So this is a circular motion of one loop tracing another loop, running around it. And so similarly, you can then actually continue your journey. So you actually see lots of circular motions in this space. And that already happens in the neighborhood of a rose, right? So this space Yn has non-trivial topology already in what you could call the star of a rose. So that's kind of interesting. So the neighborhood of a rose, the star of a rose. Oh, there's my it's already non-trivial. So how to think about, I already mentioned this motion inside the space. So how do we think about this space really as something topological and not just as an abstract realization of a category with morphisms and stuff? So here's how you can think. Actually, this also applies to the spine, but it also applies to Yn. So the way you think about these things is not as volume 1 metric graphs. That's not appropriate. So recall that the definition of the category was the vertices are marked graphs and the morphisms, that is the edges, are blowing down forests. So here's one way of doing that. If you have a forest, a subforest, you can think of that, that's a collection of edges. You think of them as having length 1 before the blowdown and length 0 at the end of the blowdown. And you realize that edge as blowing all of these edges down, shrinking them in length continuously and simultaneously. So that would be the diagonal. Here's an example. Here's a graph with a forest of 2 edges. And if you shrink them simultaneously, you walk down, oops, let's use blue for that. You walk down this diagonal, just shrinking them down to 0. And you could also just shrink one of these edges down, and that would give you this edge. And then you could shrink the other edge down, that would give you this edge. And you could reverse the order. And you see there are 2 triangles in my complex, and I can glue them together to get a square. And this square, really, the points in this square, if you look at this, you can think of them as being like copies of this graph, but one of the edges has one coordinate as the length, and the other edge has the other coordinate as the length. So, yeah, yes?
I might have missed something, but I'm confused about the lower left graph that has Betty number 5 instead of 3.
Oh, that is because I missed. This is not correct.
Okay, that helps with the confusion for me.
Thank you. So what do I want? I want to have, oops, I want black, first of all. So I need this little thing. So coming from here, I collapse the red edge, so I should get a little theta graph like that.
I can agree with that.
And I guess, yes, okay, that's better, isn't it? Okay, so, but the points in the, that was the, right. So the points in the, thank you very much. The points in the square are just, well, you read off the length for these edges as the coordinates of this thing here. So this gives you the length of the edge A, and this gives you the length of the edge B. And then you just draw the corresponding picture, and there's sort of the point in outer space, roughly, right? It's not a volume 1 metric. Now this is really about metrics where the edges have length at most 1, and if you blow down all the edges that have not length 1, you don't change the fundamental group. You don't change the fundamental group. So the edges of length not 1 have to be a forest. That's the rule, and that's how you can parameterize the space. What happened? Oh, that happened. Most theory and dimension. Now that is going to be, I'm thinking about what I could reasonably put in 3 minutes.
I'll make it 5 if you need to.
Now, I guess this is I mean, there's a new section starting. Maybe that's a good point to stop.
That works too.
Then I'm happy to take questions.
Yes, let's start with Zoom again. If there are any questions on Zoom, somebody might want to ask. If that is not immediately the case, you can always write them in the chat or just start talking later. Are there questions in the audience? Otherwise, I'll ask a quick question. So, so now the complex that you're getting, this cube complex, or I guess, is that already the right dimension, or do you have to contract something down?
No.
Do you have like a quick picture of that or something that gives us an indication of what you're contracting?
So the strategy is the star of a rose. That is already in the top middle panel, right? These loops running around other loops. That's actually that is actually a nice little space. Oops, didn't I write that down? So anyway, so these things we call these cactus graphs, and it turns out that that the space is homotopy. The star of a single rose is homotopy equivalent to the space of cactus graphs, and that's dimension n-2. So the star of a rose can be realized as an n-2 dimensional space. But in order to glue roses together, you need to, it's really the faces along which you want to glue them that you have to work on. And those are a priori 2n-4 dimensional. That's the link of a rose. And we managed to get that down to 2n-5 dimensions. And we do that by looking at the descending link and pushing in free faces. And the main argument is about the existence of those free faces that you can use to push in. So it's really just looking at the links the descending links, the links that connect a star of a rose to all the previous roses that you already have. And then you look at and that complex is a priori 2n minus 4 dimensional, and you have to get rid of 1 dimension. And you do that by pushing in 3 faces.
All right, cool. Are there any other questions? So before anybody leaves, we're going to thank Kai-Uwe again in a second. I just want everybody to stay for the picture that we're going to take now. But let's thank Kai-Uwe again more. Maybe Kai-Uwe can stop sharing for a second, or for now, yes.